Hello class, welcome once again to our lecture. This is a continuation of our previous video. Okay, so here are the other example that will help us understand more on the concept that we have discussed in the first part of the video. Okay, so we have here charge Q1. Charge Q1 equal to 7 microcoulomb is at the origin, and charge Q2 is negative 5 microcoulomb is on the x-axis zero point 0.3 from the origin. Okay, so assuming this is our x and y axis, origin meaning the intersection of the x and y axis. Alright, so the problem here is A, find the magnitude and direction of the electric field at point P. So this is our point P. Okay, so we are asked to find the magnitude and direction. So magnitude and direction of the electric field at point P. So at this point P. Okay. So at point P. So at this point. So meaning sorry, won't allow class. Just okay. So at this point. So it means at this point, class. This is our point P. All right. So here are the givens from Q1. This is 0.400 meters. The distance, and from Q1 to Q2, so this is 0.300 meters, and from P to Q2 is 0.5 or 0.500 meters. All right. So to solve this problem, so we have used the formula of the electric field, which is given as E1 equal to K times Q1 over R1. All right. So substituting the given, so take note that this one is our key here. This is already calculated, class. So our K is already calculated from the formula. This is 1 over 4 pi times the epsilon sub 0. Okay, we have here the value, the standard value for this. And when you calculate this one together with this value, that is 8.85 times 10 to the minus 12. So you'll get K here, which is equal to this one. Okay, then you have Q1 now as given in the illustration. So our Q1 here is charged at this point, the origin, that is 7 microcoulomb. Okay, so this is the one. And then the distance between P and Q1, that is 0.4. So we have this, then square this. So we got here 3.93 times 10 to the 5 Newton per coulomb. Okay, so that's our E1. Then finding the x component, the x component of E1, the x component of E1. So this is our E1, class. Okay, so the x component of this, since this is 90 degrees, so Ex is A1 cosine of 90, that is equal to 0. So that's equal to 0. Okay, so but we can get the vertical component of E1. So the vertical component of E1 is simply use sine, E1 multiplied by sine of 90. So it gives us 3.93 times 10 to the 5 Newton per coulomb. So this is just the same as this. So it has no horizontal component, but it's vertical. So in other words, our A sub 1, meaning the electric field at this point, is just equal to the x is the vertical component of it. Okay. Now for E2, so we'll consider this charge here. All right. So the same value for K. This is the same value for K. Then Q2 is the charge at this point to minus, but you take only the positive value of this. All right. So absolute value of this is equal to positive 5 microcoulomb. Okay. So substituting, and the distance, the distance from this one to P, that is this. So that's why you have here the denominator 0.5, then you square it from the formula. This is square. Okay, so we got here this Newton 1.80 times 10 to the 5 Newton per coulomb. Then to solve for the angle theta, okay, so the angle theta here, so we can solve this theta here. We are considering this part class of the illustration. Okay, so this angle theta here is just the same as this angle theta here. So we can solve for the angle theta so that we can get the horizontal and vertical component of this charge, of the electric field of this charge. Okay, which is equal to A sub 2. Alright, so cosine of theta from our trigonometry. So cosine of theta is adjacent, okay, adjacent over hypotenuse. So that's why we have here cosine of theta, or cosine of theta is equal to adjacent over hypotenuse. So we get it, we get here 0.6. Okay, so now let's solve. We can now solve for the horizontal component or the x component of the electric field of this charge A sub 2, Q sub 2. Okay, so horizontal, so we have to take cosine, cosine. So A sub 2x, meaning the horizontal component of this electric field, is equal to A sub 2, meaning this one here, then multiplied by cosine of theta, but the cosine theta is already solved. So we got this one, and therefore we have this answer. So that is equivalent to 1.02 times 10 to the 5 Newton per coulomb. Then to solve for the vertical component, vertical component of this electric field, vertical component of this one, or this is just equivalent to this. Okay, so again we use the trigonometry here. Sine of theta opposite over hypotenuse. So this is our theta, so opposite this side over hypotenuse. So that's why we have 0.4 over or divided by 0.5. So we got here 0.8. So we can now solve for the vertical component of the electric field A sub 2. So the vertical component A sub 2 y equal to A sub 2 sine of theta. So our A sub 2, we got A sub 2 already here, which is this one. So multiplied it by sine of the theta, which is this, given us 0.8. So we got here negative. So negative 1.44 times 10 to the 5 Newton per coulomb. So to sum up all the, to get the resultant of all the horizontal component or the x component, so you just add, we have the total x component part of the electric field. So we have E1 sub x or E sub 1x plus A sub 2x. So E sub 1x, so we get E sub 1x equal to 0. Okay, this is 0 because A sub 1x here, A sub 1x is equal to 0. Okay. Okay, so this is 0. So that's why we have here 0 plus e sub 2x. So this is e to sub 2x. So we get this. Then adding the 2, so we get this one. So this is our total or the resultant of e sub x. Okay. Now for the vertical components, so the summation of all the vertical components. So again, this one is in our calculation. So this is, as you can see here, a sub y. Okay, so is a1 sub y, a1 sub y plus a2 sorry, e sub 1y plus e sub 2y equal to, so this one is 0 because the horizontal component a1 sub y. So this is a1 sub y, which is 3 point something. So I think a2 sub y, as you can see here, this is, okay, this is the one, a2 sub y. Okay, so the first part now, the first part is equal to 0. A1 sub y is 3.93. A1 sub y. Okay, so don't include this one, class. Okay, so A1 sub y is calculated as this 3.93 times 10 to the 5 Newton per coulomb. Okay, this one. Then A2 sub y. A2 sub y is this one, which is negative, negative A2 sub y. So it means that it goes down. The vertical component of this one, as you can see here, so it's going down. So that's why we have negative. So adding, so this is plus negative something. Then when you combine, so you have here this. Okay, and then to find the magnitude, so the magnitude is just the square, the square root of the sum of the squares of the horizontal components of the electric field and the square of the vertical component of the electric field. So take note, these are the resultant, right? These are the resultant electric field, and you square that one, you square and then take the square root, so that is now the magnitude. Okay, so we got here the magnitude of the electric field is equal to this one. Now for the direction. So for the direction, okay, so as you can see in this picture, class, in this illustration, so we have E here. This is, we're talking of this E. So this E now. So we have calculated this E, that is the resultant. Okay, so now we are going to find the phi. No, this is the angle phi. So this is the angle phi here. So this one, we're talking of this angle. Okay, so to get this angle, so we just use the formula that is tangent. Tangent is equal to opposite over adjacent, no? Opposite. So our opposite is this one. This is our a sub y. All right, and adjacent a sub x, this one. So a sub y here. So we get a sub y, which is this one. Then over adjacent a sub x. So the a sub x here is the one that we have calculated a while ago, which is this one. It is 1.08 times 10 to the 5 Newton per coulomb. Okay, so this unit cancels. So what is left is this one divided by this. okay, because they're just the same, right? So they're just the same, so when you divide them, so it's 1. So you just take care of this one. You 2.49 divided by 1.08, and then take the inverse tangent of the ratio of this one, so we get 66.6 degrees. All right, so F, which is the equal to the AQ, no? AQ meaning the product of the electric field and the charge. So electric field is 2.71, okay, multiplied by Q. Q is as given the problem. So as given the problem, okay, so this is find the force on a charge of, so this one, so we have to make use of this. So that's why we have to multiply the resulting Q, resulting E, which is the electric field, by that given 2 times 10 to the 8 coulomb. So we got here the force. Okay, so the force, which is what kind of force is that? That is the uh, electric force, no, electrostatic force. Okay, so we got the force here, which is equal to 5.42 times 10 to the minus 3 Newton. Okay, so I hope you understand this current class, and let's proceed immediately to the next problem. Okay, so this problem class is for you to practice, no, using the same concept, but let's try, if we can do it here. Okay, so for your practice class, so try to solve these two problems. Okay, so now to give you an idea on how to solve this, I'll show you an example here. Okay, so our example is again, we are having here the electric field, or the field of an electric dipole. So point charge Q1, Q2, point charges Q1 and Q2 of plus 12 nanocoulomb and minus 12 nanocoulomb respectively are placed on, or placed 0.10 meter apart. So this combination of two charges with equal magnitude and opposite direction is called an electric dipole. This is called electric dipole. So compute the electric field by Q1, the field caused by Q2, and the total field of point A, and also B at point B and C at point C. Okay, class, to make this video shorter, no, I'll cut this video here and then just make a separate video for the solution of this problem. Okay, so see you again in the next video. Bye.